Yeah, so as Mark mentioned, my name's Gina. I'm a PhD student in the Atmospheric and Oceanic Sciences Department at CU. And during my second year of the PhD program, I was able to take part in the MOSAiC expedition, flying uncrewed aircraft, also known as drones, to collect data about the Central Arctic atmosphere. And so I'm going to talk about for this presentation, what is MOSAiC? Basically give you an overview of what that was, and talk about what it was like for me on the expedition, as well as what we have learned about the atmosphere and the sea ice using our drone data that we deployed during MOSAiC. So so just as an overview, MOSAiC stands for the Multidisciplinary Drifting Observatory for the Study of Arctic Climate, which was a year-long expedition lasting from about September 2019 through October 2020, in which the icebreaker Polarstern was frozen into the sea ice near the North Pole and set to drift passively across the Central Arctic, popping out of the sea ice in the Fram Strait for an entire year. So you can see this diagram here that's color-coded by different portions of the expedition. So you can see the drift started up near the North Pole, and there's these 5 different colors of this line here because there were 5 different legs of the expedition. So throughout the year, they brought scientists in and out of the expedition to kind of transition who was up there doing the work. And also throughout this entire year, there were 5 primary science teams. The team atmosphere, which was what I was involved with, as well as ice, ocean, biogeochemistry, and ecosystem. So each of these teams was doing different research about their category of science, just to learn the most comprehensive understanding of the Central Arctic climate system that we have to date. And if you're interested in any blogs or websites to know more about MOSAiC, there's a few links that I provided at the bottom of the slide. So the motivation for MOSAiC comes from the fact that I think we all know that the Arctic is warming faster than anywhere on the rest of the planet. And this warming is expected to continue by the end of the 21st century. This warming has a lot of impacts on a variety of things. One thing that I think as NSIDC we're very aware of is that sea ice in the Arctic has declined dramatically over the past several decades, and this trend is expected to continue. But why do we really care about what happens in the Arctic? It's kind of far away for us, most of us living in the mid-latitudes. So why do we care? One primary reason is that temperature differences between the poles and the tropics drive global weather and climate. And as the Arctic warms, this temperature difference is going to become less drastic. And so things are going to change. It's not going to be what we expect. This kind of has already been leading to a lot more extreme weather events that we see in the mid-latitudes. Also, melting ice sheets cause sea level to rise, impacting billions of people. When the sea ice melts, that's not going to be necessarily what impacts the sea level rise, but most importantly in the Arctic, the Greenland ice sheet, a lot of the processes that we measured during MOSAiC are also relevant to what's happening in Greenland as well. And so all the science that was done on MOSAiC is to help us understand how the Arctic is changing, so that we can better incorporate this data into models and maybe understand how it might impact the global climate system in the future. And the work being done right now is really just the beginning. We're expecting all the data collected during MOSAiC to be analyzed for decades to come. So just some fun facts about MOSAiC and the participants. These numbers were put together before the expedition, so some of them in reality ended up being a little bit different, but I'll share anyway. So the expedition was planned for about 390 days, just over a year. Aside from the Polarstern, which is the primary icebreaker where the expedition took place, there were several additional icebreakers that were used to bring the scientists in and out to transition between the legs. There were 20 different nations involved in the expedition. You can see all the different flags at the bottom there. And this includes about 300 people that were actually, or so I'll say, about 300 people, I guess, were on just behind the scenes, helping with the science to support the 600 people throughout the year that were on board the Polarstern. Throughout each leg of scientists up there was support by a logistics team that did things like polar bear guarding, watching out for polar bears on the ice to make sure we're being safe, as well as, not to mention, the wonderful crew on the Polarstern that fed us and made sure that we were comfortable and safe throughout the whole time. lots more facts, and you can find all this online too if you just Google the MOSAiC expedition and go to their primary website. So this is a little schematic that shows what the scientific observatory was supposed to look like for MOSAiC. So you have the Polarstern here kind of located as a base where all the rest of the stuff happens off of, and you have all sorts of different operations happening on the sea ice. You have Met City, where the meteorological measurements are taken, Ocean City, Ice City, I think you can assume what happens there, Balloon Town, where they have their tethered balloons, as well as just a logistics area where you can kind of pick up snowmobiles if you need to get what you need for your time on the ice. In reality, here is a picture of what it looked like. This is actually towards the end of my time on the expedition, so some of the instrumentation had been removed from the ice at this point, but you can still see this tent out here is Balloon Town, Ocean City, this logistics area where we have all the snowmobiles and other equipment. So now I want to talk a little bit about our team and what we specifically did for our project on MOSAiC. So as I mentioned earlier, as Mark mentioned, we were using uncrewed aircraft or drones for our measurements during MOSAiC. So I want to recognize all the other people involved in this team: Heist DeBoer, John Casano, Radiance Calmer, myself, Brian Argro, Steve Borenstein, Michael Rhodes, and Chris Choate. And Dale Lawrence, Jonathan Hamilton, and Avi Doty. Several of those people were also in the field throughout the campaign, but a lot of them were providing support from back home in preparation for the expedition and just supporting throughout. So the primary science targets for our UAS work were kind of threefold. So first of all, we wanted to understand the subgrid scale variability in the coupled system and the ability of today's modeling tools to capture features resulting from this variability. Next, we wanted to understand and observe variability in sea ice and its contribution to energy transfer in the ice-atmosphere-ocean interface. And lastly, we want to understand the impact of coarse vertical resolution in models on the proper representation of complex boundary layer structures in the Central Arctic. So we ended up using two platforms to kind of answer these questions, that being the DataHawk 2, which is located in the figure in the upper left, and the HELiX. And I'll get into a bit more detail on each of these aircraft, but just as a general overview, both of these aircrafts can kind of contribute to each of these things, looking at atmospheric structure, though the DataHawk is primarily the one used for looking at atmospheric structure, things like meteorological conditions. The DataHawk and the HELiX can both be used to look at spatial variability. So DataHawk more focused on spatial variability of atmosphere features over a feature of interest, such as a lead, which is a section of open ocean when the sea ice splits apart. But the HELiX can also give us a sense of spatial variability of sea ice conditions. And I'll get into both of those more in a few slides, but those are the two platforms used for our study. And I'll also give you an overview of our team's deployment schedule. So originally, there were supposed to be 6 legs of scientists throughout MOSAiC, transitioning every 2 to 3 months. And we were supposed to have 3 teams of scientists out there. So John Casano and I during leg 3, between February and April, Heist and Michael at leg 4, and then Jonathan and Radiance leg 5. But as we all know, something happened worldwide in about February, March 2020, that being the pandemic. And that kind of impacted a lot of things, including the MOSAiC expedition. So suddenly, all the plans we had to kind of transition between leg 3 and the subsequent legs of MOSAiC kind of all went out the window as aircraft operations that we were planning to use were no longer available. And it was difficult to get icebreakers to help with these transitions. And so in the end, legs 3 and 4 kind of got merged into just extending leg 3. And then there was a new leg 4, which started a little bit sooner than was expected. So that kind of canceled out one of our teams of scientists, unfortunately. And so it was just the 2 teams out there. So John and I, we operated the DataHawk. And then once Radiance and Jonathan arrived to MOSAiC, they started operating the HELiX as well. So another figure of the MOSAiC drift, labeled and color-coded by the different legs. And now we overlay where the UAS operations, UAS standing for uncrewed aircraft systems, where these occurred. And so you can see that the Datahawk flights, which are showed in green, were happening for a longer time as we were operating that aircraft for the whole time that we had any team members out there. So we completed 89 flights, or about 43 hours of flight time, with measurements as far north as 87 degrees. And as far as I know, this could be potentially the farthest north drone operations for scientific purposes that's occurred, especially at the time of year that we were doing this kind of in the middle of winter. It's pretty unique data set that we were able to get. And then you can see that the HELiX flights, which are shown in red, those occurred in a later portion of the campaign, and they were able to complete 36 flights and about 9 flight hours. So lots of data from that. And now I'll get into a little bit more detail of each of the aircraft that we flew, what we were able to learn from those different platforms, and the different types of analysis that we've done with the data since returning from MOSAiC. So I'll start off with the HELiX. So the HELiX is a hexacopter. It's shown in this figure here. Has a weight of about 12 kilograms and can fly for about 20 minutes. The measurements that the HELiX takes are upwelling and downwelling shortwave radiation, which it measures with 2 pyranometers. And from that, we can calculate the albedo of the sea ice. It also has a multispectral camera for surface imaging, this red edge MX here. It also can measure pressure, temperature, and relative humidity with the Vaisala RSS 421. There were a few different types of flight patterns that were done with the HELiX. They could do a grid flight at about 10 meters to measure spatial variability, could do a hover at 3 to 5 meters altitude, which gives you data over a specific feature of interest, such as a melt pond. If, let's say, you're interested in the albedo of the melt pond, can do a hover flight, and also for a profile up to 100 or so meters, which tells you about the integration of more surface features into the albedo measured by the HELiX as we increase in altitude. So then the Datahawk is a fixed wing aircraft. It is about 1 meter in wingspan. It's a lot lighter than the HELiX. It's only 1.8 kilograms. It has a longer endurance time, so it can fly for about 40 minutes. However, if it's really cold out, then you don't generally get that maximum time. You might get more like 20 to 30 minutes instead. So the Datahawk measures temperature, pressure, and humidity that it can do with the Vaisala RSS 421, as well as the SHT 85 sensor. It also can measure wind speed, which is calculated using measurements of ground speed, airspeed, and the aircraft position. So it takes measurements from a few different instrumentation on board and can calculate that afterwards. We can measure the IR temperature. So there's an IR sensor on the top and the bottom of the plane, and that can kind of give us a general sense of what kind of features we're flying over or under. And also it measures turbulence. So there's a fine wire array located inside this little thing here that's measuring turbulent temperature and wind. So there's also a few different flight patterns that we did with the Datahawk. The one that we did the most was a profile up to 1,000 meters, and this samples the full boundary layer. So this figure on the right shows what a typical profiling flight will look like. We're just flying in the circular pattern between the surface and 1,000 meters. Can also do a loiter at a fixed altitude, and this can measure the temporal variability. So let's say you have an air mass moving across where you're measuring. If you loiter at that altitude for long enough, you can kind of capture those changes. And also racetrack over a feature of interest. Most specifically, we were interested in leads. So this can show the spatial variability of the atmosphere due to that surface feature. And the center figure shows a flight pattern of a lead flight. So you can see that we're doing some profiling on one side of the lead, flying across the lead, and doing some profiling on the other side of the lead to figure out what the difference is. And I'll also share a very quick video of the Datahawk taking off. This was our first successful Datahawk flight, just to show you what it looked like out there. And there's a little bit of sound. Hopefully it goes through. 3, 2, 1. So perhaps you could see in that video that the takeoff, wasn't the smoothest ever. We almost hit the ground, but we're able to maintain enough airspeed and eventually get up. And that's because there were a lot of unforeseen challenges that we had when we first got out there and first started operating the Data Hawk that we kind of had to learn how to adapt to. And so that, after that, we had a lot more smooth takeoffs, didn't risk not making it into the air. So some of these primary challenges were the pretty cold winter temperatures. So the lowest temperature during flight during leg 3 when John and I were out there was minus 35 degrees Celsius, pretty cold. That led to us just having to kind of adjust some of the things we were used to being a certain way when we were practicing in Boulder to how it could work in these cold temperatures. The ice conditions were also a bit challenging. So during leg 3, when John and I were out there, the sea ice was very dynamic. It was frequently opening up with different cracks and leads and then creating ridges afterwards. We also had a fairly fast drift speed of the ice, so we kind of have to adapt our flight operations to that as well. And this is a picture showing one of the days when we had the worst cracking of the ice. And this tent over here is where we did our drone operations and where a lot of our equipment was located. And I took this picture from the ship. So you can see there's quite a bit of obstacle to get over there. During leg 4, the ice was less dynamic, but more so it was just melting because it was the melt season during the summer. And they had an even faster drift speed of the ice, a maximum of 1 knot one day. And sometimes also the ice floe was also rotating and not only drifting. So it was really difficult to kind of maintain where the aircraft is and make sure that you're flying it in the right spot. Also, yeah, as I mentioned, there's a lot of melting ice during leg 4 in the summer. So this decreased the available landing area and also a lot of fog in the summer, which makes it kind of difficult to keep an eye on the aircraft and make sure that you're staying safe if you have fog roll in during a flight. But despite all these challenges, we were able to collect a lot of data, and we've published all of the data sets that we collected on the Arctic Data Center. So we have 2 data sets for the HELiX, the top one being the albedo, so the measurements from the pyranometer, as well as the meteorological measurements. And then the second being the multispectral imagery data. So if you're interested in using any of this data, you can find this online. Also, we have the Data Hawk 2 data is published. This is just all of the different measurements that taken with the aircraft. And there's also, we have a data paper out, which explains the methods used throughout the campaign to collect all the various different data. So if you're interested in using this data, I would highly recommend reading the data paper that accompanies it so you can kind of understand the data a little bit better. So now I'm going to give a quick overview of all the different types of analysis that we have done with these 2 different platforms. So first of all, I'll talk about some of the analysis done with the HELiX data. So as I mentioned, the HELiX can measure albedo. So one thing to do is to look at a frequency distribution of albedo during a flight. So in this example, this figure on the top left, this is the grid pattern flown during one flight and color-coded by albedo. So you can see when we have a higher albedo versus lower, that might be when we're flying over just bare ice versus melt ponds, for example. And then speaking of melt ponds, using the multispectral imagery data, we have created orthomosaic images to map the surface and calculate the melt pond fraction during a given flight. So most of this work has been done by Radiance Calmer. She's been analyzing the albedo and melt pond fraction, and Jonathan Hamilton created these orthomosaics for us to use. Another thing Radiance has been doing is to kind of figure out how the evolution of the melt ponds has changed with time. So primarily just looking at this figure on the right, we have the flight date and the day from onset of the melt pond formation versus melt pond fraction. And the blue dots are the first year ice and the orange dots are the multi-year ice. And what's interesting here is you can see that at this point in time, the first year ice melt pond fraction decreases. So the hypothesis is that there was a drainage event that occurred after July 10th. So a lot of that melt water, it drained and melt pond fraction was lower after that. There's also been a lot of analysis that we have done with the DataHawk. So as I mentioned, one of the flight patterns that we completed was a lead flight. So flying upwind and downwind of a lead and kind of seeing how the air mass is upwind and downwind might have been impacted. So on the left, we have temperature profiles upwind in blue and downwind in red of the lead. And then on the right, the same, but for the absolute humidity. And looking very close to the surface, you can see that there's potentially a signal. We have warmer temperatures and higher absolute humidity downwind of the lead. And so we hope to do some further analysis of this in the future to kind of tease out some of the impacts from the leads that are occurring in the Central Arctic. This is a paper that I actually recently published that we've using primarily the DataHawk data as well. So what we did was we were testing the efficacy of different atmospheric boundary layer height detection algorithms using the drone data from MOSAiC. So since we have these really high resolution profiles from the DataHawk, we can use it to subjectively identify what is the atmospheric boundary layer height, and then can use a lot of automated algorithms and see if they're able to accurately identify that boundary layer height, kind of determine which is the best method in the Central Arctic. And our conclusions led us to say that the Bulk-Richardson number method, especially or particularly with a critical value of 0.5, is the best method for boundary layer height detection in the Central Arctic. There's also been some work done by Ulrika, or led by Ulrika Eggerer, who was working on estimating turbulent energy flux vertical profiles using the DataHawk measurements as well. And she has compared this also to measurements of turbulent fluxes from the radiosondes, a tower, and from the Beluga tethered balloon. And this work is in prep, but hopefully be published in the not too distant future. And then lastly, the work that I'm currently working on is using the DataHawk data as well as radiosonde data from the entire year of MOSAiC to understand the boundary layer structure in the Central Arctic and what are the different thermodynamic and kinematic processes that are most important. So since we only have the DataHawk data from Lakes 3 and Lake 4, which were approximately March through July of 2020, this only gives us a small picture of what happened over the entire year. So that's why we supplement this work with the radiosonde data, which provides profiles at least 4 per day for the entire year to give us a really holistic overview of the boundary layer for the entire year. And we're focusing here on things like the boundary layer height, low-level jets, which are a low altitude local maximum in the wind speed, temperature inversions, and we also can supplement all of this information from some near surface data from the meteorological tower that's pictured here on the right. It can give us things like 2-meter temperature or friction velocity, and then also supplemented by some other measurement platforms. A ceilometer can give us information about cloud cover, and also a radiation station that was located on the sea ice near this tower can give us some idea about the surface energy budget. And with all of this, we're kind of compiling a climatology of the boundary layer, the different processes that impact it in the Central Arctic. And one way that we are doing this analysis is using self-organizing maps. And so the next part of this talk is going to be focusing on what is a self-organizing map and why is it useful? What can it be used for? And for this part of the talk, my main hope for you to take out of it is to understand what are self-organizing maps and what is their value. And I'm going to use my work as an example, but I'm going to try not to get too much into the nitty-gritty of the atmospheric boundary layer, because I know perhaps a lot of the people in the audience here are sea ice scientists, not boundary layer meteorologists. So my overall hope is just to understand self-organizing maps. So what is a self-organizing map? So a self-organizing map, or a SOM, which I'll call it from here on out, is an unsupervised neural network algorithm which determines the different patterns present in the training data and groups the data to minimize the squared difference between the data and the SOM pattern. So maybe that's a lot of confusing words for now, and I'll get into some examples. Because it is unsupervised, the algorithm is mostly doing everything by itself, but there are some user-specified parameters to start. So first of all, you obviously have to tell it what is the training variable you're using. So what is the feature of interest for you? Then you also have to tell it what is the number of patterns you're interested in. So the number of nodes that the SOM will pop out. And it might take some tweaking for you to look at some SOM outputs in order to understand what number of patterns is what makes most sense for your example. You also specify training length, learning rate, and neighborhood radius, which all kind of go into how the SOM is organized and how, as it's training itself, little changes can affect other nodes, things like that. So why is a SOM useful? So a lot of data sets that perhaps people in NSIDC or other folks may use may have a lot, very large data set and have a lot of values you're looking at, terabytes of data, but it's really hard to kind of understand what is the meaningful results when you have that much data. So a SOM is really useful for reducing large data sets into meaningful patterns, and can also be used to identify relationships between processes of interest within these really large data sets. So I showed two figures kind of to show, to help introduce the benefit of a SOM. So this figure on the left is just temperature profiles from radiosondes from MOSAiC from March through May. And you can already see, there's lots of different temperature structures going on here, but it's really hard to tease out too much in terms of patterns. And this is only March through May, it's only a few months. So imagine looking at this for 10 years, how are you going to possibly understand the important processes? Well, a self-organizing map can help with that. We also show a figure here that is looking at the low-level jet speed versus boundary layer height from radiosondes during MOSAiC. And this is a bin scatter plot. So primarily, most of the data is down in this portion of the figure where we have the more yellow colors, which means higher bin counts. So it's really kind of hard to tease out the really important relationships which are happening this portion of the plot when we're looking at a scatter plot with all the data. So SOM is helpful to kind of narrow down the amount of data you're using to understand relationships. So I'm going to come back in a second to looking at an example from MOSAiC using SOM analysis. But before I do that, I want to share one other example of a SOM analysis from some previous work that doesn't have to do with MOSAiC, but could be of interest to the NSIDC community. And that this type of analysis could be really helpful for others to use in their work. So this SOM was trained using the wintertime horizontal near surface wind data from ERA Interim and WRF between 1997 and 2007. And the result is 35 nodes, which each represent an observed wind pattern. So that's what we see in this figure with all these subplots. Each of these subplots represents a SOM node. So what that means is it represents an observed structure in this surface wind around Greenland. So then what is done once we have these SOM patterns, then each actually observed wind pattern is attributed to each node or to the node with the SOM pattern to which it is most similar. And then we can learn things like the frequency of each pattern that's seen in the training data or in the observational data that we're interested in. And a lot of SOM analyses are done with this kind of latitude, longitude versus surface feature type of thing. So in this case, that surface feature is the near surface wind, the 2D wind vectors around Greenland. But the SOM, the way that we do the SOM for the MOSAiC work is actually looking at profile data rather than a surface map. So it looks a little bit different. So in this example, and this is the work that I've been working on for the past few months and will be putting it eventually into a manuscript, is learning about the atmospheric boundary layer structure from MOSAiC radiosondes and training a SOM using profiles of virtual potential temperature gradient to best identify different atmospheric boundary layer structures and stabilities. So the result here is 30 nodes, which each represent an observed profile structure. So each of these 30 subplots tells you a type of boundary layer structure that is present in the Central Arctic. And then each radiosonde profile is attributed to the node with the SOM pattern to which it is most similar. So for example, looking at node number 1, this profile of virtual potential temperature gradient, there are 89 radiosondes which look most like this. But it's really hard, I don't know if there's that many boundary layer meteorologists in this audience, but if you know much about the boundary layer, it's kind of what we like to really look at to understand the boundary layer structure is the virtual potential temperature profile rather than the gradient profile, which helps us to see, where there's an inversion, where there's a potential neutral layer. So then once we've trained the SOM, we do what we call mapping, and that's mapping a feature of interest onto the SOM. So as we had in the last figure, for each of these subplots, the black lines are that same SOM pattern. But now what we've done, and I'll use this first node as an example, is we've taken all 89 radiosondes in that node and calculated the average virtual potential temperature gradient in pink and the average virtual potential temperature anomaly profile in the orange. And so what this results in is us to really clearly see the 30 different most commonly seen boundary layer structures in the Central Arctic. And this can help us do things like determine stability regime for each node. So we've developed some thresholds to determine the different stability regimes, and that's what is color-coded on the outlines of each of these subplots. And you can see what they mean in this key on the left. And I know it's a lot of letters to look at, so I'll just summarize by saying, basically, as we go from the top of this list to the bottom, we're going from more stable to less stable and then near neutral with the orange colors in the end. So this reveals that in the boundary layer, or in the Central Arctic, the boundary layer expands from strongly stable to near neutral. We don't really have unstable cases. The next thing you can also do is, if you've trained the SOM with a certain data set, but you're curious if you're curious where some observations from another measurement platform might fall in that SOM context, is you can map the other observations onto the SOM. So that's what we've done here. We've taken all of the DataHawk profiles and determined what SOM node they fall in by calculating the least squared difference between each DataHawk profile and each SOM and the SOM nodes, to kind of attribute each DataHawk profile to a SOM node. And the benefit here is then now we can see if somebody's interested in using the DataHawk data for things like the turbulence measurements, which would be really interesting. You can kind of see, okay, what different boundary layer structures have we measured with the DataHawk? So how might that be useful for what I want to know? The next thing that you can do once you've trained your SOM and you've mapped your variable of interest is what we call compositing. So that's taking other variables that you want to know something about in the SOM context and kind of relating those to the SOM nodes. So what you see in this figure here, for all the circular points, for each SOM node, we've taken the median low-level jet speed and the median boundary layer height. So you'll maybe remember this figure from a few slides ago, which shows the same variables for all radiosonde profiles. It was really hard to kind of tell what's really going on there. So now using the SOM, we've pared down that data into just 30 data points that are shown with the circles. And you can see that the range on the X and Y axis for this figure created using the SOM is the same range as what is encapsulated by the highest bin counts of the data when you plot all of it. And this kind of shows that low-level jet speed is increasing as boundary layer height increases, which we could get that from this big plot. But what we couldn't really get from the plot with all of the data is that the relationship is a lot stronger for these weaker stability cases. And that once we're above a certain boundary layer height, and once we have these more near neutral cases, when the low-level jet speed doesn't actually make much difference. And we've also overlaid this figure with the same information from all of the DataHawk profiles, which are shown with the triangles. And this just basically shows that the DataHawk data does agree with what we saw from the SOM. And the last thing that we have done with this analysis, and it could be done with a SOM analysis, is once you look at your SOM, you can understand the range of different features that are present. So in our case here, the SOM revealed the range of different stability regimes observed by the MOSAiC radiosondes. And so this allows us to then regroup the profiles by stability regime to further tease out some of the details hidden in the data. So what we show here is a box and whisker plot of the two primary variables that kind of impact stability in the Central Arctic, that being the net radiation and wind speed. And we can get some pretty cool results out of this. So again, moving from left to right on the box and whisker plots, we go from our more stable cases to less stable and eventually near neutral with the orange. And we can see one of our primary takeaways is these very shallow mixed cases. They have a higher radiation than the weakly stable cases to the right of them, suggesting that these very shallow mixed cases are radiatively driven. Then looking at the figure on the right, we see that we have higher wind speeds for our weakly stable cases, whereas we don't have that for our very shallow mixed. That suggests that the weak stability is wind driven. And then looking at the near neutral data, you can see it has high net radiation and high wind speeds. So in order for us to have a near neutral boundary layer in the Central Arctic, we kind of need both high radiation and high wind. And conversely, for a strong or moderate stability case, we kind of need low wind speeds and low radiation. So doing the SOM analysis helps to lead us to these cool results. So now to talk a little bit less about the nitty gritty of the atmospheric boundary layer, I do just want to make the final point. Throughout this talk, I've kind of talked about the HELiX data and how it measures the different albedo and melt pond fraction of the sea ice, and the data hawk and radiosondes and what they measure about the atmosphere. But I just want to remind myself and remind everybody that the atmosphere and sea ice impact each other. So both of these analyses come together in the end and really should be considered together to get the holistic understanding. And so I put some few points up here on how the atmosphere and sea ice can impact each other, but I'll just point out a few important ones that I have thought about a lot. For example, synoptic scale patterns in the weather and atmosphere, such as high winds, let's say, for an Arctic cyclone, can impact the sea ice thickness and extent. Such a synoptic scale weather event, like a cyclone, can open up a lot of leads, and we actually saw this quite frequently when I was out on MOSAiC. And from these leads, we have a heat and a moisture flux from the open leads into the atmosphere. Conversely, when we don't have the open leads, and instead the sea ice is fully covering the ocean, then the sea ice insulates the atmosphere from oceanic heat, and that kind of helps to create this pretty frequent inversion layer that we have in the atmosphere. And temperature inversions have been shown to constrain warming in the Arctic to the near surface layer, and is kind of one contributing factor to Arctic amplification being felt very close to the surface of the Arctic, and then thus impacting further sea ice melt. So these are just a few points that kind of lead us back and forth between how the atmosphere and the sea ice affect each other. And I just want to keep thinking about both of these components of the climate system together. And so to end this talk, I'm going to spend a few minutes talking about what life on the expedition was like. Now that I've talked about science for the last 40 minutes, I'll end with a little bit more fun note. First of all, this picture was taken when myself and the rest of the folks that were on leg 3 with me first saw the Polarstern. So we had spent about a month sailing north on the Dronitsen from Norway, and at last we arrived to the Polarstern, and we had this very beautiful setting. So my time on the expedition, just to start off, was a ton of beautiful scenery, which was awesome. Then, as I mentioned at the beginning of the talk, myself and the rest of my UAS team, we were part of Team Atmosphere. So on the Polarstern, there were lots of other folks that were involved in the atmosphere team, doing things like operating the tethered balloon, launching radiosondes, maintaining the Met Tower and the other instrumentation out at Met City, as well as a lot of instrumentation on the bow of the deck. So during leg 3, this is a fun photo of all of us from the atmosphere team hanging out on some chunks of ice, and then from leg 4, the atmosphere team as well. And it was really helpful to have this team of other folks that were out there to kind of help you and support you, and you could do the same for them to hopefully ensure that everybody's able to achieve their science goals. So what did a typical daily schedule look like on MOSAiC? So the day started off by a fairly early breakfast at 7:30, followed by a flight coordination meeting. So this meeting would look like the UAS operating pilots would meet with other people who are interested in airspace operations. So this would generally be the helicopter pilots and any other scientists who are hoping to use helicopter operations for their science that day, and also the tethered balloon folks as well. So we would just discuss, what does everybody want to get out of the day? First of all, are the weather conditions such that it's possible for you to do your science goals, and then kind of talk about how we're going to coordinate so that everybody can get done what they want to get done. Because when the helicopter is operating, we couldn't necessarily be flying the drones unless we were very sure that they were going to be very far apart from each other. So this is the things you discuss. Then we have a morning general meeting at 8:30, which entails anybody that's planning to go out onto the sea ice that day comes together and basically recaps what they had discussed the previous night on what they're planning to do, make sure everybody has the polar bear guards that they need, make sure they have the snowmobiles that they need if they need them, just to make sure everybody's set for the day. Then throughout the day, there's intermittent periods of time where you're allowed to go onto the ice and work. And those are kind of broken up by the different meals. So we have lunch, cake break, mid-afternoon, and eventually dinner. And if somebody did want to be out all day through those lunch and snack break, you could definitely coordinate that and bring your own lunch and be out there. Then after dinner, we have an evening general meeting at about 6:30, in which you discuss what your plans are for the next day. Make sure, it's kind of starting the conversation so that the meeting the following morning, you can make sure everybody has the resources they need. And once that meeting is over, 7:30, a full 12 hours from when your day began, it's time for evening activities. Now, a lot of times the evening activities entailed fixing the drones if something had gone wrong that day. Here's a picture of Jonathan with the HELiX trying to work on something. Not sure quite what, but that was the most common evening activity. However, sometimes nothing would go wrong on the plane that day, or you were really fast preparing it for flights the next day, and you could have some time for some fun things. So some of the fun activities we were able to do include evening walks out on the sea ice. You can see us hanging out after just going for a walk out on the ice. Sometimes there were some sports that occurred, some people playing soccer. I unfortunately didn't partake in that particular game, but it looked really fun. There was a swimming pool on the ship, so we could play water basketball, shown here in the bottom left, which was really fun. The water is pretty cold though. And then something that we did actually a few times is pictured in the bottom right, is we had a barbecue out on the deck of the ship. So the crew would prepare the grills for us and give us a bunch of raw meat, and you would just go out and cook your own meat however you liked it, with all of your jackets on because it could be pretty cold. And this was a great way to just kind of socialize with other scientists, but also the crew was invited to these events, so you could get to know some of the crew members as well, who you were living and working with for the many months. So it was really nice. And so I'll end this talk just by sharing my favorite highlight of my time on MOSAiC, which was a camping trip that we were able to do. So we got some of the emergency tent and sleeping bag equipment and walked out from the Polarstern. You can see we're a good distance away from the ship out here. And we set up camp and got to sleep on the ice for a night. It was really cool for me was if you stood in a certain spot behind this ridge here, you couldn't see the ship at all. And it just felt like you were really out there in the middle of nowhere, and you could hear the ice moving. And throughout the course of the night, we could see the sky changing from what you see here around midnight with this midnight sun to full overcast by the morning. So it was, really cool to kind of see that transition as we were taking turns bear guarding throughout the night. And with that, I will just want to acknowledge the National Science Foundation, CERES, NOAA, the Alfred Wegener Institute, and the NASA CAMI program for supporting my work on this MOSAiC research and also supporting the MOSAiC expedition in general. And I'm happy to take any questions.
All right, well, that was great. Gina, have a nice round of applause, a virtual round of applause. That was great.